Okay. All right. So I'll start, and as I said, we'll take a breaks at some random time for about 10 minutes when the camera's issues are resolved. So I'm going to start with calculus of interventions. We'll continue from where we left off in yesterday. Okay. So recall that what we are dealing with is a structural causal model. Sorry, switch my pen. We're dealing with a structural causal model. So this consists of the structural equations along with the independent random variables which are driving these structural equations. So that is the model. There's a DAG associated with it, vertices and edges, and there's a Markov factorization over the D random variable. This is the same setting which we are dealing with from last time. Okay? And today's stuff again is primarily following the elements of causal inference by Peters et al. And the causality book by Pearl. We talked about various types of interventions yesterday. For the most part, I'm going to today stick to only two types of interventions, either atomic, meaning set one of the random variables J is some deterministic A, or a simple random intervention, meaning set one of these equations to be just an independent random variable. Doesn't have any parents or any such thing. We could do other things as well, but for almost the entirety of what I'm going to talk about today, we'll just stick to these cases. And the goal is to compute the intervention distribution, but using conditional probabilities from the observed distribution. So I keep saying often that using data from the observed distribution. What I really mean when I say using data from the observed distribution is I have infinite samples on the observed distribution. So using the observed distribution, I can compute the joint. I can figure out the joint distribution. I can find all the conditional distributions associated with it. That's really what I mean by using data. It's not a finite sample issue. It's everything I'm talking about right now is all population case, infinite sample. Okay. I'll get to the finite sample either depending on how long the camera either this today or tomorrow morning. Okay, so in this case, we have two DAGs, the original observational DAG, C, and C tilde, which is the interventional DAG. So these are the illustrations of the two things we are looking at. This is the original DAG. Xj is the node on which I'm going to do an intervention. So what do? I cut all incoming edges to that node and set this to be some new random variable independent of everything else. Good. Let's write the joint distributions for these things. For the observational distribution, it's some joint distribution over the D variables. Okay? And because of Markov factorization, you can write this as, for example, this node, let's say it's XR, then this node will appear as X probability of XR, condition on its parents of R. Right? That's the kind of terms you'll get for this one. For each one, you will get a term, which is probability of that given its parents. Look at the product form, and that's the observational distribution. Again, we have seen all this over the last 2 days. I'm just summarizing all this so that the notation again becomes clear for today's lecture. We are doing an intervention. So what happens? I want to write the joint distribution for this model. If you look at this particular node in both of them, its parents have not changed. And therefore, the term associated just with this one is unchanged both in the original DAG and the interventional DAG. So for this part, if this is node R, then I would in both of them I would have a term. So P C tilde. Okay, let me use a different color. All I'm trying to say is P under the original model of XR given parents of XR is equal to P C tilde in the new model as well, XR given parents of XR. That's all I'm trying to say. Okay. For those terms, nothing changes. Good. But for this one node, things do change. For this node, here it was P of XR given its parent, whereas here it is just the distribution of NJ tilde. It's something different. Okay, so we are writing that out. In the C tilde model, the joint distribution, again from notation, C tilde is nothing but C with a do on that XR is For every node other than j, the corresponding factors would be exactly the same. Yes. Sorry, IT is here, so I'm going to take a pause for 5 minutes. I'm going to mute the microphone and we'll continue. I'll restate this thing and start from there. We'll just stop till this is sorted out. Thank you. Yeah. So unfortunately, we will not have video today, but hopefully you can hear my sound and the screen sharing is working, so we can just work with that if that's okay. Let me those are the two essential pieces, so hopefully that's okay. All right. The sound is coming through fine, right?
Absolutely, yeah.
Okay, perfect. Then let me just continue from where I left off. So, as I was saying, the intervention distribution factorization is exactly this for all nodes other than j. For the jth node, all we are doing is putting p tilde xj, where p tilde is the marginal distribution of n and the new random variable I put in nj tilde. Fine. So it is almost immediate. I mean, there is from everything we have set up so far. And suppose we had a deterministic intervention, then p tilde is not the distribution becomes trivial. It just becomes an indicator. The distribution is equal to a with probability 1. That's all. It's a singleton distribution, which we can then represent by just an indicator function. So my notation is this symbol is always indicator. Indicator, if I say xj equal to a, this is basically equal to 1. If when xj equal to a, xj equal to a, and 0 otherwise. Okay, just a 0, 1 random variable. All right. So we have the 0, 1 case with the indicator. Fine. So these two are called the truncated factorization theorem. If you see this word, that's all this thing means. So this is where we stopped yesterday. So this so far is just a recap. We just continue from here now. All right. Now, the first thing is qualitatively we saw that conditioning is the same as do for nodes with no parents. Okay. So let's actually show that happens. Suppose x1 is a node with no parents. Okay. Then what I want in the original model, let's look at the original observation model and let's see what conditioning happens. So so I want the joint distribution on the other x2 to xd, condition that x1 equal to a. This is equal to, and I'm dealing with this deterministic case that it's always equal to a. This is the case I'm looking at. Okay, just a atomic intervention, which is that means just this is simply the joint distribution of a and all the others divided by the probability x1 equal to a. Now I'll do the factorization for this. This is remember x1 has no parents, so in the factorization it just appears as p of p, just the distribution for that particular variable. For everything else from the factorization, px given pai. So this px1 equal to a cancels, and so all you get for the joint distribution given x1 is a is this product from I equals 2 to d of pxi given parents of I. And here, when we are looking at parents of I, there's a slide. I've just told you what the parents of AI are, but they also have values. So implicitly, the value, whenever this particular node happens to be a parent, that value should be set to a. So this thing is a function of a. Okay, I've just sort of hidden that notation. Now let's do the same for the intervention distribution. Okay, so this is for the do x1 equal to a. So I again want x2 to xd, but in this new distribution. So how do I do this? I will look at, I will just marginalize out. So since I want the distribution x2 to xd, there's no conditioning here, remember. Okay, there's a do that has happened here. So I look at the joint distribution x1 to xd in this new model and sum over all values of x1. Of course, because I do x1 equal to a, this is, and it's a hard intervention. This is basically nothing but this summation has two terms. One when x1 is a and when x1 is not equal to a. but all the other not equal to A terms are 0 because that cannot happen. So all I get is for x1 equal to A. And again, factorization is the same for everything else. So you get from 2 to the of xi given parents of xi, where x1, and in this parents of PA of I, x1 is always A. And therefore, we see these two expressions are exactly the same. Okay, so that is for x1 with no parents, the conditional distribution, the original model, is the same as the intervention distribution in the second model. This is what qualitatively also it was clear when we talked about it. Now this is just formally writing everything. I'm just writing all the nuts and bolts of it. All right.
Please explain the first equality again. Well, why does no this after now from 2? Yeah.
This one?
Yes. Why is it equal to marginalizing on X?
This is some model, some joint distribution. Let's just put back C tilde. Suppose I ask you, forget about the C tilde model. In some particular model, ask you to find Q of X1 when I give you the joint distribution of X1 and X2. What would you do? You'd look at Q of X1 comma X2 and sum overall X2. That's all I'm doing. So this is just notation. It looks like I'm doing, there is no condition, it's just confusing looking notation. This is just, I'm doing this. All this is indicating is that I'm dealing with a new model. That's all it's being.
Just in the new model, if I looked at X1 up to XD, it would not be this marginalizing because you're only looking at X2 to XD.
Yes, exactly. That's the point. I'm looking X2 to XD, not X1 to XD. Maybe that's what you were asking. Okay, yeah. I'm looking from X2 to XD. So the one extra here is this X1 is, so maybe I should make this, since you asked, let's just make this thing a little more clear. That makes it much more explicit that there's an X2 as well. So let's go back to our kidney stone example. And we said, remember in the first time we talked about the example. I'll recap that example once more. But we said that we want to figure out the causal effect. And we just said that it can be done. So now let's actually calculate it using just this. Okay. So the example is the following. There are 700 patients. There are 2 treatments, treatment A, which is open surgery, and treatment B, which is a small puncture surgery. And the Simpson's paradox we saw was the overall success rate for treatment A was worse than that for treatment B. However, for patients with small kidney stones and for patients with large kidney stones, treatment A is better. And this was the paradox we did. And so this gave the really weird statement that if you don't know the size of the stone, then treatment B is better. However, if you know the size of the stone, whatever the size is, treatment A is better, which is an absurd statement. Okay. So let's fix this now. Okay. What we really want to understand now is the causal effect. After all this discussion over the last couple of days, we realized that that's what we need to compute. We need to sort of somehow deal with this confounding effect. Okay. And the confounding effect happened because the size of the stone not only affected this recovery rate, but also the treatment. That was the real problem. Implicitly, the doctor was using the size of the stone to make a decision, and potentially for hard cases, only there was treatment B not used because it perhaps treatment B is safer or cheaper or whatever. Okay. But we want to somehow deal with that effect without doing new experiments. Of course, a simple fix for this would be the following. I'll just do a randomized trial. I will again go back, throw away all this data, and just do a new randomized trial. The doctor prescribes A versus B, and then collect new data, and we should be easily able to see there what is going on. But we don't want to do that. We want to do it from just observational data. Good. All right. So given this, my variables treatment is 0 is A and 1 is B. Size of the stone 0 is small, 1 is large, and recovery 0 did not succeed. The surgery succeeded. 1. These are my variables, and our goal is to compute the following 2 things. What is the probability of margin on recovery that recovery occurs? So this is the marginal on the R variable. Okay? The probability that recovery is equal to 1 in the setting where we did treatment equal to 0. What does this mean? This means in this graph, I want to cut this edge and set this equal to 0. And I want to compute in this particular model, what is the recovery? And I also want to compute the other one, which is I cut this, set treatment equal to 1, and then look at what happens here. These are the two things which I'd like to compute. It's clear? So let's do this calculation. So this is just a do. So in the do treatment equal to 0, I want to figure out the probability recovery equal to 1, which is there are 3 variables here: recovery, treatment, and the kidney stone. Okay, so it's a joint distribution in this new model. Again, we are dealing always with this new model right now. Okay, C tilde model. RTZ of recovery is 1, treatment is 0, and the stone size is 0. Plus recovery is 1, treatment is still 0, and Z kidney stone is 1. There are not 4 terms here. There are only 2 terms, because treatment equal to 1 is a 0. That indicator will take care of it, and you don't need to deal with 4 terms. There are only 2 terms here. Okay, good. I know it's obvious, but I'm just stating all obvious things out. Okay, then what do we have here?
So this is like you fix treatment equal to 0 and you want to calculate the probability of recovery, right?
Correct.
So it's the sum of like when stone is equal to 0 and stone is equal to 1.
Correct.
Shouldn't there be a multiplication of probability of stone equals to 0? Like a
No, this is a joint distribution. This is not conditional. This is the joint. So again, this relates to the same question he was asking earlier. So if I want to figure, if I have, forget whether this, what model this world is. Okay, forget C tilde or whatever. Suppose I have a joint distribution on x1 comma x2.
Marginalizing over Z.
I'm just marginalizing over Z. That's all. That's why I was saying there's actually 2 more terms, but they're both 0 because those terms will have a 1 here, t equal to 1 there, which cannot happen in this one. Okay. So it is just a margin. I'm just taking the full joint distribution of the triple and marginalize, writing the marginal as the sum, as the double summation or the other alphabets. That's all I'm doing. All right. So now so far I've just been only in the new world. Now let's go back to what do we know from the old observational world and the new world? Well, in the old world, for the recovery random variable conditional in its parents, that conditional distribution is unchanged in both. Why? Let's look at this. This variable's parents in the old world or the new world. In the new world, this is gone. But as far as this is concerned, this conditional distribution hasn't changed. So this is exactly the same. And again, this is same for the Z. It has no parents. So actually, this is trivial. The parents actually don't. The marginal on Z in the old world and the marginal on Z in the new world is exactly the same. Okay. These are 2 things which we have. So now, what is the recovery when do treatment equal to 0 of this thing? Well, this is what I have, right? P RTZ 100 is 1 given 00 times P of 0 times, because indicator treatment equal to 0. We are only, because treatment is always equal to 0 in these 2 things, just 1. Okay. I mean, there's nothing, this is all standard probability. There's no, the non-standard thing is C here, not C tilde. I should have used C tilde everywhere. Okay, that's really what has happened. This was a C tilde here, but here I have C. Okay, and that was because of this. So this is where we are reusing the fact. So the correct statement, the standard total probability theorem will give you this with the tildes. The total probability theorem I'm using is that along with the fact that I know these things are the same. Okay.
Please explain why they are same, like probability in C and C tilde.
Good. Look at the value of Z. This is, let's draw 2 pictures. This is a C model, correct? The C tilde model is the following. That is C tilde model. Look at in this model, remember what's the Markov factorization? P of R given Z comma T. This one also, the Markov factorization of this will be, for this recovery variable, the parents are exactly the same. There's no change in the structure. So this local conditional distribution doesn't change in either of these models. Same for Z. Its children may change, but its parents haven't changed. Z is only affected by its parents, which is a null set, and so nothing has changed. So this goes back to this again goes back to this basic observation we wrote. It is how did we get 2? We are just using 2. That the new distribution is everything else is the same except for that one place where we did the intervention, where I put an indicator. That's all I'm doing. And because of that, this is the same as this. So that means here I can replace these C tildes by C's. Okay. And now I can compute these quantities. All these are known because I have the data and I can, right? And so in particular, how do I estimate this? This is just now, I have observational data. If I have finite number of samples, I will just condition on 0, 0, meaning just look at those samples which are 0, 0 and find the fraction of samples where this is 1. So this is just traditional conditioning. Okay. And in infinite sample setting, I know these quantities. So therefore, from the table which we have, so this is the table, we can compute all those quantities, because this is the C, this is a joint distribution on C, so I can figure everything else out here. So from this table, I can compute this, I can compute this, and compute this. For example, to compute PZ of 0, I just need to ask what fraction of patients had small kidney stone, and just look at the table and just count out how many. That's all. Okay. So every one of these can be calculated from observational data. Once you do that and you put it in, what you get is when you do treatment equal to 0, the probability of recovery is 0.832. And when you do treatment equal to 1, the probability of recovery is 0.782. Again, neither of these numbers appear in that table, but these can be computed in this way. So this is essentially saying open surgery is better than small puncture surgery, that means there is no paradox. This is actually the key calculation. If something is confusing, I'm happy to talk through it once more. Yes.
I have a few questions.
Yes.
So first, a very basic question. So every time we do a do operator, are we essentially saying that we are just removing all the incoming edges into that mode on which we are applying it to operator? Is that a right statement?
Do operator means in the structural causal model, you're changing some equations. Okay. That's what do operator is. Now we need to see how this do operator. Now, if I'm doing atomic do operation, meaning I'm setting a particular value, in that specific case, it is the same as removing all the edges and setting that value. But I could do so many other types of do interventions. Okay.
Essentially, in the series of those equations, as to how they relate to each other, we are changing some of those equations.
So the correct answer is, in this structure, whenever a do is done, your structural causal model has been altered. That new model induces a new graphical model that entails a new joint distribution, and that is the distribution we're dealing with. This is the correct sequence of statements. In this special case, it is just in the graphical model is eliminate those edges and just set that value, and the factorization is just put an indicator for that one term for the atomic thing, right? And yeah, one more question.
So in this example, can we say that essentially what we were doing was that we were adjusting for the confounding effect of the size of the kidney stone?
Correct. That's exactly correct. We are adjusting for the Z, for the size of the confounding effect. The Z is affecting both. This is called adjusting, exactly. But what we are doing is removing the effect of the size of the stone on the doctor's decision. That is the only, but we are not changing the size of the stone on the recovery rate, because see, that is really why this is it's conditioning. If I condition on Z, it would affect both. It would affect both the doctor's treatment decision as well as how the body is going to deal with maybe small stone versus large stone surgeries. Okay. Do operation is saying I will correct for quote unquote the doctor's decision, but not change the other link. The other edge is still left. So the size of the stone does affect the treatment affect the response R.
So here we can say that we are looking at R given T independent of whatever the kidney stone size is.
We are looking at this. Whether you call it, I don't want to use words like independence because they are loaded words. So I basically want to just say, this is what you're looking at. Okay, it is a new graphical model, and we are trying to understand the compute marginal distributions in this graphical model. That's what do is do. Right. Okay.
Question. So you are assuming, in this particular example, you are assuming that the table that's given to you is according to the SCM that's drawn.
Exactly. I am positing a generative model for my world. So maybe there is some other thing which is bothering stuff.
Right.
Good. That's why I said I am proposing, this is just in my view, a modeling framework, which all modeling frameworks are assumptions. The assumptions here is that this is the SCM. Okay.
So last week, if I saw that table, I would have thought of that as a joint distribution. Now here we are not thinking of it as a joint distribution. We are thinking of it as an SCM.
Exactly.
There's a distinction between these two.
Exactly. There's a generative model. I am having more than a joint distribution. I'm having a generative model, which basically tells me how I can do what interventions mean. But you can think of it as a joint distribution, but you should say that there is no other extraneous variable. The SCM adds the fact that there is nothing else which is affected. So there may be a third, maybe the place where this surgery, not just the kidney stone, I'll give you an example, okay? Suppose maybe in Europe, maybe somehow everything is affected differently from the United States, okay? So it will not just be a Z, there's another variable U, which is sitting here, which will give a different SCM. So putting the SCM essentially tells me a generative model for this relation.
Not just that. Let's say there are no extraneous variable.
Okay.
Even then, there's a difference between SCM and joint distribution. Because for the same joint distribution, I could draw a different graph. That's what you told yesterday, right?
I could do this. You're saying, yeah.
Then
I am also putting a structural model saying stones affect treatment, and the treatment does not affect the stone. For example, there are some implicit assumptions we make when we reason about this. Okay, does the treatment somehow affect the size of the stone and therefore the recovery or something, right? All these kinds of, these all could happen. They'll lead to different SCMs. Here we are putting a joint, but joint distribution, we are imposing a joint distribution and a Markov factorization, you can see. Okay, a little bit more as well the SCM does, but also a particular factorization. This particular equations are being assumed, right? This is the factorization that we're using. Correct. Okay. So now hopefully this is this clear? Okay.
We have time for one more question.
Of course, yeah.
So I have a kind of a thought experiment there in the example that you just showed. So let's say we had one more variable, gender.
We had one more variable. I'm going to repeat because I think people in the Zoom cannot hear. So suppose there's one more variable, gender.
Let's say there's one more variable, gender, and we know that gender is going to influence the size of the stone.
Okay.
It might also treatment, also recovery. I mean,
okay.
I'm just going into a possible clinical scenario.
Okay.
My question is that how would this graph would have to be transformed?
It's a mess. So you are talking about latents. I pointed out that I think I made this comment, but maybe I didn't emphasize it.
But gender is known. I mean, gender doesn't have to be latent, right?
No, in this data, it's not there. So it is latent.
I see. Okay.
Okay. If you have gender as a data, you could again reanalyze all this stuff. You would do a do on X. Let's see. If you had a gender variable which was observed, it's affecting everything, then that is easy to deal with. What will I do? I will do Z T something comma G equal to something. I can do these kinds of do's. Okay. And then I can start doing, essentially now you have two variables on which you're intervening. So there are now a whole family of joint distributions. Each has an entailed distribution. You can reason on each you can reformulate your question on what happens in this case, what happens in this case. Does gender affect things alone? Does gender and treatment affect? All these questions can be asked, and it will come down to these kinds of you factor things out, write it a bunch of conditional probabilities, and whichever you can get from the original data, you can do it. If you had this table, it's not a matrix, then it will be a tensor with the gender data as well. You could get all this thing and you can sort it out. The problem is if gender is a latent variable, then it's a completely different story. If you know that gender could affect, but I don't have access to gender, then it opens up then things can be done. You will need either bounds or you will need some other way to analyze that. It's not even clear whether this DAG representation is the right one. In fact, it isn't, because as I said, these are not closed under marginalizations. So when there's a latent variable, then you get into trouble there. So I'm happy to talk offline. For this though, I will avoid latents for the most part. Yeah.
Sorry, going back to the previous discussion, so you said that so we have this Markov factorization that we are working with.
Correct.
But SCM is more than a Markov factorization, right? Because like the other graph that you drew with the arrows reverse, that has the same Markov factorization. I mean, the multiple for a given Markov factorization, there are many graphs you can draw. That's what
it also says a functional relation. It says the independence of the random. There's a whole bunch of we are using that generative model to get this thing. Okay, which is why this model of causality, this is the Perlian causality, has an explicit generative model, which is a structural causal model, from which everything, once you have that and you buy into that, you've gotten all the you can analyze everything using quote unquote traditional probability on a bunch of models. If you don't want to go through an SCM, then that's a very different world. I'm not going to talk about that.
Okay, then there's a philosophical question here, right? So you have the.
I'm not going to answer any philosophy questions. You avoid philosophy.
You have the table. Why should I think of it as
good? I'm not going to answer that.
You gave me these numbers.
So Shiva's question is, why is this the right structural causal model? You gave these numbers. There is infinite amount of discussion online, and I don't even want to say anything about any of it. I told you in the first lecture, this is a model which sounds plausible, and I'm not going to justify this model beyond it sounds reasonable. People do. Again, I don't want to make any inflammatory statements here, so you can go online or you can follow this up yourself.
But suppose we did randomized clinical trials.
Yes.
And then we actually assign this treatment A or treatment B independently, then we would know that probability is like explicitly. Then there is no confusion at all.
That is
There's no belief anymore on any model.
Yes.
Okay.
Yes. These models are useful because I can actually do intervention distribution calculation using observational data. But that's a powerful translation. All right. So hopefully the example made it clear what kinds of things we are trying to do here. So let's now make this more formal beyond the example and talk about adjustments. Oh, I forgot to say one last thing. So what is average causal effect? This difference between in the do world, when I do treatment equal to 0 and treatment equal to 1, I get potentially different answers. That difference is called the average causal effect for binary treatments. Okay. And if this was equal to 0, then you would know that the treatment you would interpret it as the treatment has no real causal effect on the recovery. Okay.
Let's say the Z variable stone size was not discrete, it was continuous smooth. Your formulation is still, how will that?
Yeah, you can do stuff with continuous, but I will avoid it here. You can do Gaussian, these things, well, nothing really changed. With Gaussian models, you could do these kinds of things. Then how do you deal with the reasoning? It's not conditional probabilities, you need to go through PDFs. But the rules with PDFs are similar and things can work out, okay? You will talk about densities. It's all doable. I'm just avoiding it because it just keeps my life.
It's a small question. So if you had, let's say T had 3, it could take 3
okay, 3 values.
How would you define average causal effect in that case?
So look at the night light example last time. We had 3: low light, high light, no light. T has 3 values, and then I will get 3 values. I'll get 3 numbers. Right. How would you define it? Maybe you can say, is the expectation different from any one of them? Okay. I mean, you can make way. So we talked about it last time there was a theorem. It says there's an average causal effect if any two are different. Okay, but this is just a quantification of what it is. Now you can start quantifying it in different ways.
Okay, thank you. I have a question. So, like while calculating with do, you take do treatment equals to 1. Then you calculate this probability with respect to all the possible size of kidney stones, right? With z equals to 0, z equals to 1.
Correct.
So that doesn't explain the removal of paradox. Like you can still have paradox if you calculate do treatment equals to 1 and kidney stone equals to 0. You take both these variables as do.
Yeah, but that all that is saying is treatment and kidney stones will affect things. But the kidney stone should affect. So it's the paradox is here that this is having a different trend from this. That is really the paradox. Now that issue has been resolved. Maybe we can discuss this offline then. Okay. All right. So we have now shown an example of how to go about this calculation. Let's now talk about a more systematic way of doing these adjustments. Okay. And I also want to connect this back to whatever we did with graphical models and all. This calculation was just straightforward. It was just looking at two distributions, factorizing it, and we just saw from one to the other. We want to go beyond this. So I want to talk about adjustment. Informally, first I'll state it informally, and then we will sort of formalize it. This the phrase adjusting for a variable z, or z is a valid adjustment, means that we can compute intervention probabilities, but using conditional probabilities by conditioning on z and their intervention variables. Okay, that is, so we want to reason about a new world, but using data from the old world. Okay, this statement will become the example we saw roughly what we are doing. Let's actually go through this adjustment. This can be interpreted, I think, as just a new total probability theorem that relates interventional distributions and observational distributions. So if it was a standard total probability theorem, when you study in undergrad class, all the probabilities are from the same universe. Here, we can switch universes, we saw as an example, because certain conditional distributions are the same in the new and the old universe. So we can put in C tilde instead of C in some places. Okay, so we start with the C tilde probability we want to compute and use a standard total probability theorem in the C tilde world, and then replace some conditionals with the C world and do some algebra on it. You'll get a new total probability theorem. That's really what adjustments are. Okay, okay. So so I'm going to define a valid adjustment set. Okay, so C is a causal model. And say we intervene on node k, meaning do set do xk, the random variable xk, to be set to little xk. And let's consider any j not in the parents of xk. Okay, some other node. And finally, consider a set of variables z, subset of x1 through xd, which is not either xj. This is where you are doing the intervention, and this is where you are doing the intervention. And this is where you're observing. Okay. So in our example before, xk was the treatment and xj was R, recovery. Okay. Then z is any other set of nodes. Here z was just the kidney stone size in the example before. So a collection of variables is called a valid adjustment set if the following holds. Look at the marginal on xj in the new world. That is equal to the sum over all z, the conditional of xj given xk and z, okay, times the probability of z, sum over all z. This is not what you see in the total probability theorem, because in the total probability theorem will have xk as well here. Okay, this statement is clearly true. What I've done in blue. This is just what I've done in blue is this traditional total probability theorem. What is left here is not the traditional total probability theorem. We have done two changes. Replace here C tilde to C, and here we have replaced C tilde this by just C of this. So this is what, if you can find a collection of variables Z that satisfies this equation, then Z is called a valid adjustment set.
The left hand side, is it C tilde or C?
In the left hand side meaning? I don't know whose left hand side. Which side? The C do or yeah, that is C tilde. C tilde is the same as C do. I'm using in my talking. I'm going to, let's go back to the where we had this. Yeah, C tilde is the same as C do always. Okay, I'm just using tilde for a shorthand. Otherwise, I have to say C do. All right. So this is the definition of a valid adjustment set. So in the kidney stone example, the valid adjustment set was just the size of the stone. It was and we adjusted this. We adjusted for the size of the stone to compute the average causal effect on recovery. Of course, in general, we see that C do is not the same as conditional. This is again, I've said it like n times through this discussion. And this inequality is what is colloquially called confounding. Okay. If the conditioning is not the same as do, then this is confounded. That's what you mean when you're saying confounding. And to correct for this, we need to find a valid adjustment set so that you can compute interventional probabilities from observational data. Because you see, if you did have this equation, you're done. Because this is what you care about. Okay, this is the interventional probability. These are all observational data. So the valid adjustment set is a sufficient condition for computing marginal intervention probability in a particular node from observational data. It's not necessary. I guess you are going to ask if there's necessary and sufficient. We will talk about necessary and this is a sufficient. This is a sufficient condition. In fact, it's strictly a sufficient condition. We will show something else. Do calculus actually generalizes this stuff, but I'm going to get to that in 10 minutes or so. Yeah.
So why should Xj not be in the parent of Xk to calculate the probability? Why should Xj not be in the parent of?
Because it's upstream. What is it in the causal model? What does that mean? I'm trying to, the intuition here is doing something here. I want to see whether it affects something or that. By parent, it cannot affect, it's upstream. Okay. So typically J is downstream. You are interested in this only when J is downstream of K. Question.
The adjustment set is a function of the Xj, right?
No, it's just a. Where am I? Here I've just defined adjustment sets of some collection of variables. If you can find a collection of variables, there's no unique adjustment set for a problem. I have a graph, I have a collection of nodes, I have an Xj, I have an Xk. You give me a set of Z which satisfies this equation, then that is a valid adjustment set. Maybe Siva gives me a different set of Zs which satisfies this equation. That's also a valid adjustment set. I'm not making any statement here about uniqueness.
What I'm saying is that you have to know both Xk and Xj to give me the Z. Xk is not enough.
Yeah, I mean, it depends on everything, right? Because of course Z cannot have Xj and Xk. So in that sense, I'm not sure I understand your question, I guess.
So what I'm saying is that Xj is just the probability, the random variable you want to find the probability, right?
Yes.
So change that.
Of course, it will change. The valid adjustments will be very, very different potentially when you look at the effect somewhere else. Yeah.
Can we say that until we have adjusted for every Z in the valid adjustment set, the effect that the treatment effect that we might be calculating could be biased or confirmed? So let's say there are 5 or 10 elements in the valid adjustment set.
Then you need to condition on the vector.
Oh, yeah.
Yeah, you need to uncondition the vector. Okay. It is not a scalar problem. It's a vector. Z could be a vector, in which case you need to search over all possible values of that vector. Okay. So in the example, we just had a scalar adjustment. You can't do one scalar at a time, if that's what you're asking. You can't marginalize with one at a time. It's a whole vector.
So that would be like
this Z is actually a z-dimensional summation, if that's what you're. So whenever I put a summation with a vector, it means it's a vector dimensional summation.
Then the resulting effect would be like the true causal effect.
Yes. Yes. Question?
Understand how this all modeling relates to randomized control trial. In randomized control trial, you have, let's say, different confounder variables. You try to randomize all these. You want that in both the groups, you should have enough number of both the confounder variables so that they don't affect and you only see drugs. Now here in structural causal model, let's say you have observation data. What it is doing, it is somehow trying to do the same objective. Am I correct at the intuition level?
Exactly. So his question was, what is the connection between this and randomized control trial? Randomized control trial is to actually just implement this model I've drawn in a blue box and just collect data straight from that. And then use just regular probability on this. This approach is saying, I only have data from this, but I would like to simulate a randomized control trial. Okay. In some sense, not simulate, but compute about. So randomized control trial, then you directly do calculations with it, you're done. You don't need any structural equations or models.
If there, let's assume there are many other confounder variables like.
But then you need to, then the same, it's elephants all the way down, as it were. You can start from whatever the randomized control trial is your observational model and then do something else below that, or it's turtles all the way down. I guess that's the right statement, not elephants all the way down. Okay. But you just take this and do one step down, and that's all there is. Okay. Let us see. So I've defined what a valid adjustment set is, and defined confounding. Oh, it's almost 11 o'clock already. So maybe shall I do 10 more minutes, or because we started a little, what do you want to do? Should I continue, or I'm fine either way. Do you want to?
I think we can take a 10-minute break either now or later.
Yeah, we last about 5 minutes. But this is a long stretch, the next stretch. Okay, then we'll just take a 10-minute break and we'll recover. We'll restart in 11:10. Actually, 11:10. Let's take a 13-minute break. 11:10 local time is when we will start again. Thank you. All right. So remember, what we are looking for is a valid adjustment set. Meaning, I want to, in the new world, in the do world, I want to find on the response xj. I want to but all the computations are from the old world. And this is the total probability theorem I'm looking for. Good. So the roadmap now is the following. Can we find some sufficient conditions on Z such that I can satisfy that equation? That is, how do you find a valid adjustment set first algebraically? Question one. And the answer is going to be something called invariant conditions. I'll get to that in a second. Is it always better to use a bigger adjustment set? Meaning I have an adjustment set. I'm not sure if something else should be included. Let me just throw that in as well. Is that still a valid adjustment set? No. Adjustment sets are not, they don't have this monotonicity property. We'll show that. So this goes back to actually day one's last example, where I did a downstream, I put downstream and some weird things started happening. So there is you should not adjust on as many variables. Variable selection is actually important. Okay, and Bergson's paradox is an example of that. Then we'll talk about what property we're looking for algebraically, and then we'll say, can we do this graphically using d-separation? Can I look at the structure and say, hey, this should be the adjustment set, just looking at this graph, and that is characterizing it this way and putting all these things together to the adjustment theorem of graphs and d-separation. So that is my roadmap for the next half an hour or so. Yes.
Let's take it a step back. The reason we like having adjustment sets is that we can get the interventional distribution using the observational distributions.
That's the only reason why we care about it. If you could actually do a blind trial, you wouldn't need any of this. Right. You want to get in, the reason you want a valid adjustment set is because this equation is true. That's all we are shooting for right now. So these are observational, this is intervention. And I just want to relate that without doing any new experiments. That's it. So it's this 4-step roadmap. The first step is the algebraic property. A sufficient condition would be the following. Where is the adjustment theorem I had written? Here. Let's look at in the interventional world, but we had to write this as just a regular total probability theorem in the interventional world. This would be a tilde here. This would be a tilde, this given xk. But it's an atomic intervention. So given xk or not doesn't matter really. Let's make sure that's clear. Because there's just a one variable here, I can just, this would be the total probability theorem in the interventional world. Because the condition xk is a trivial condition because it's a probability one. Xk equal to 1. In this, when I do this thing in this world, it's just 1. Right? This is nothing fancy. What I've written here is just the regular total probability theorem in the new universe. So one way of one sufficient condition is, hey, suppose in the old world and new world, these terms are exactly the same. Whether I put tilde or not, term by term, everything is the same. Then summations, all the algebra should be there. It looks like a strong condition, right? But I'm asking for every single term in this particular equation. I want the old world, the original world, and the new world to be the same. Okay. So you can see that this will be a sufficient condition because of that. But this is what is an adjustment. So coming back to your statement, that's really what we are looking for in this adjustment. So these are called invariant conditionals. So Z is a valid adjustment set if the following invariance occurs across the original observational SCM and the interventional SCM. The conditional of J given X, given where you have done the intervention, and Z, that adjustment set, is the same across before doing and after before and after doing the two worlds. And the marginal on Z is the same in both worlds. Okay. When I again use a marginal, I don't mean always in my discussion, marginal is not necessarily one-dimensional marginal, it just means less than d-dimensional. I'll just use the word marginal for any joint distribution, which is not full on all variables. I'm just going to misuse the term because Z could be a vector. I'm still going to call it a marginal. It's just not a scalar marginal, it's a vector margin. Okay. Is this clear? What I mean by invariant conditionals? So this is the motivation is exactly what I've written this down here, but it's essentially this. This is what we said is a valid adjustment. So we'll just replace every term, and then if it's term by term, these equations are true, then total probability theorem gives me this for the new world, and then I can replace each term in the total probability theorem because of this property by terms in the old world, and I'm going to get it. That's it. Good. Second step. Is it always better to have larger adjustment sets? Meaning, if Z is Z1 through ZL is a valid adjustment set, is it true that if I augment it with Z prime, that's also a valid adjustment set? The answer is no. An example of this is Bergson's paradox. Okay. This statement goes back to 1946. The statement is, why are handsome men such jerks? Okay, that's the statement. Okay, so this example 630 in the book. There's a long history of study of this stuff. You can go to the book and look at it. Really, this is because there's a conditioning going. English statements have conditioning. Okay, this statement, why are handsome men such jerks, presumably has some relationship statement buried in it, either in a relationship or not in a relationship or something like that. And so that conditioning is essentially causing these this. And what is the connection to adjustment set? We'll do this. Okay. Suppose the ground truth is, let's say there are two variables, handsome and friendly. So friendly I'm using for non-jerk jerk. Okay, it just sounds more politically the right word to use than jerk. I had to quote jerks because that's somebody else's quote, but beyond that, I will stick to. Okay, so let us say that handsome is a by Bernoulli random variable, either 0 or 1, equally likely, 0.5. Friendly is an independent Bernoulli random variable. In reality, there is no relation, either 0 or 1, equally likely. Then, of course, handsome is independent of friendly. So the statement handsome men are jerk, not jerk there should be no relation between them because they're truly independent. Okay, so the adjustment set for this is the null set. I don't need any adjustment. If I look at these two variables, they're condition independent. And remember that they're just independent. And remember that independence in the new is what we are looking for if there is no causal effect there. But let us now put in this new implicit statement in this sentence about relationship. Okay, suppose this person may or may not be in a relationship. So, and presumably handsome and friendly affect a relationship. Okay, so if they're both handsome and friendly, or maybe they're not handsome and they're not friendly, or whatever, they're in a relationship. You can build whatever structural model you want here. So there's a structural causal model buried in that sentence. Going back to Siva's question. Okay, there is some functional dependence, directions, all that being imposed here. Okay? And that imposition here is actually explicitly the model. Okay, handsome is a Bernoulli, friendly is an independent Bernoulli, and relationship is some function of handsome and friendly with some noise. I'm doing all exclusive OR here because it's all Bernoulli, so I just need to keep the alphabet on 0, 1. Yes, question.
How do you know handsome and friendly?
I don't. I'm just putting the model down. Okay, I'm just showing you. The example here is not to illustrate, is to show why this statement is not a paradox. But it's a modeling. Finally, there's a model. If you don't buy the model, then you can say, yes, there's still a paradox. Okay, but if you buy this model, then there is no paradox anymore.
But
Okay.
the model is the exact opposite of the.
No. I will show. Give me a minute. I will show you what I mean. So handsome and friendly are independent. This sentence, suppose I interpret this as, why are handsome men not in relationships such jerks? Suppose that is in parenthesis, that statement. Presumably, this statement has been evaluated on data, on a certain data set of where people are not in a relationship. What are we doing then? We are essentially conditioning on R. We have added, we have adjusted for a third. We have put Z as an extra adjustment set. And we know that condition on R, these two are very dependent. This is what we have been doing too. If you generate a Bernoulli, you generate a Bernoulli, I simply exclusive OR it. Then knowing any two states tells you the state of that one, the third one. Okay, so this is an example to show that null was a valid adjustment for H and F, but null comma R is not a valid adjustment set. So adding extra variables is not a valid adjustment. Okay, so yeah, meaning if I do H equals 1 versus H equal to 0, presumably nothing is going to. So in the do world, things will not change. But in the conditional world, things will change. Okay. All right. So this is a small example, but this just very clearly illustrates that choosing adjustment sets is important, and you can't just be, hey, I think this is an adjustment set, let me add something more. It's okay. It's not okay. You should be careful.
This again, like in why will in do world the result will be different?
2 handsome equals 1 means remove parents and compute the. I'm not in the do world, I'm not conditioning on R. Whereas the sentence is conditioning on R. So if I had somehow adjusted on this downstream node, all I'm trying to say is the following. Look at this. Suppose I said Z is R as well. Then this equation would no longer be true. That's all I'm trying to say. Okay. But coming back, this is a side issue about of whether there's some monotonicity in the size set. But let's get back to the main issue. The main issue is we want to characterize valid adjustment sets. And previously, we had this algebraic property that some conditionals are the same in the old world and the new world. Okay. I want to reason about this graphically. Okay. So let me recap something we did yesterday, and because we'll need this model now. Remember our alternate formulation of interventions using intervention variables. Okay, so just to recap that, we had, suppose this was the original structural causal model. This was the graphical model that came out of my structural causal model. Then we can, if I'm doing interventions on these nodes, I can put an intervention variable for each one of this and look at C star. And since these are now These are new nodes in this graph. Conditioning on this is the same as adjusting on, is the same as intervening. Okay. We qualitatively said that. Now you also see why conditioning and adjusting is the same. Today we saw doing on a node with no parents is the same. That's really what is that. The proof is also now done. Yesterday I didn't give you a proof. I just qualitatively explained why this is true. So this is the C star model corresponding to do's on the C model. Okay. And on the, whenever I want to do something here, meaning say, let's say I want to set x2 to some value, what will I do? I'll cut those edges. I'll just cut this edge and set this to a value. Instead, here, I'll just condition this equal. Okay. So I can do is conditioning here. Okay. So we have
that right figure.
the right figure.
Yeah. So when you say those I1, I2 are the intervention variables, they are also implicitly cancelling out the other edges, right? I mean, it's like for x2, there are two.
Yes, because you look at the equation. What is the I can stay? Yeah. This is what it is doing what you would do. Okay, what? I guess that's, I didn't mean to be a pun there, but yeah. So formally, what all we are saying is the following: look at the look at the joint distribution, the original model on x1 through xd. That is the same as the conditional distribution given I equal to 0 on x1 through xd. But I'm in the discussion, I'm going to have only one of these. IK. I'm forgetting all the others. I'm just having one. I'm just putting for one node, the node in which I want to do intervention on the node K. That's the only. So we are just augmented with one extra variable in any of the discussion below. Again, that's not required, but it just makes life easy to discuss. So, and that variable can just take two values, 0 or 1. Then it is 0. PC in the C star model, the joint distribution on the x1 through xd given ik is 0 is the distribution in the original model of x1 through xd. And when ik equal to 1 in the C star model is the interventional distribution on x1 through xd. Note there's not x2 to xd. This is the whole thing. So note that there's no marginalizing, nothing going on here. This is by construction. Okay. This construction is the following. Okay, now I will do global Markov property for C star for the model with one extra ik. Okay. In this case, D separation implies conditional independence. Global Markov property. Good. So this is the property we have. This is differing from the notes because the notation was messed up in the notes, the PDFs you have. I fixed it yesterday. So I will post the updated version soon. Okay. Pick a set Y, x1 through xd. W is some other set x1 through x of these x1 through xd, such that Y and W are non-overlapping. So these are just two non-overlapping set of nodes. Suppose that Y is d-separated from I given W. So which model are we talking about? This model. Okay, I'm looking at this graph. I'm looking right now, I'm reasoning on the C star graph. So this is my I, this node, and maybe this is my Y. Okay, and this is what I'm conditioning on, maybe. Okay, and then condition on this and this are d-separated, say. Okay, that's what I mean. So Y and I are d-separated given W. Suppose I have this property. That means in the C star model, they're conditionally independent because they are graphically d-separated. Remember the C star model, d-separation implies conditional independence. So let's write conditional independence. So I'm using this boldface for vectors here. So it's vector of Y, condition on W and I equal to 0. Because this and this are condition independent given this. Therefore, condition on this, the distribution of this does not depend on the state of this, and the state of this is only 0 or 1. So whether I equal to 0 or I equal to 1, these things are the same. Good. This is for the C star model. So therefore, PC in the C model, the distribution of Y given W is equal to the probability in the C star model of Y given W and I equal to 0. That was the connection between the C model and the C star model. There is a connection between the C model and the C star model. Okay. This is equal to, from this graphical deseparation property, I can change I equal to 0 to I equal to 1. Okay, that is this equation here. Then go back here and go back this way here. From I equal to 1, I can go to C do Y given W. So what we have proved is that if Y and I are deseparated given as W, that implies that Y and W, the conditional distribution of Y and W are exactly the same in the original and the new universe. So this is what we are looking for in all the adjustments. Okay, and this is written generically for any set vectors Y and W. Previously, I had reused language of Z and X, and I was changing the labels all the time. I was reusing Z differently. I figured it was correct what was written in my notes, but this is much clearer. This is true. I'm not making any assumptions on what this Y, W, and X are. Just suppose this property is true for a subset Y and a subset W, and an intervention I, then this is true. So now, what did we want? We wanted two properties. Remember, for our valid adjustment. In the new world and the old world, Xj given Xk and Z should be the same, and the marginal of Z should be the same. Okay. So now what does that mean here? That means in the G star, Xj and Xk, the intervention variable on top of Xk. So I is that intervention new variable we are putting on top of Xk. That variable should be deseparated given Xk and Z, and Z should be independent of I. Just translate it. So now we have taken the algebraic condition and made it a graphical condition on a new graph. Okay. So what is summary of where we are right now? The recipe is the following. Look at where you want to do the intervention. Put in one more fake variable I. Put an arrow to whatever you want. Now look at the structure. Now forget all the values on this. Now ask for these two properties. Suppose you're intervening on node J. You're intervening on node K. This one is one of the. It's a new parent to node K essentially. Okay. Node K may have other parents as well. I've just added one new parent. Then ask whether that parent and the target are deseparated. When I've conditioned on the child node Xk and the adjustment set Z. And check if Z and I are deseparated. Test without any conditioning. If these two are true, then Z is a valid adjustment set. First condition comes from this, second condition comes from this. I've just copied down here what we'd asked for, like just before just at the beginning when we talked about what a definition of a valid adjustment set is. Yeah.
So at a high level, this is actually very simple. All we want is those two equations.
Yeah.
And then once you look at this bigger graph with the I variable, then you can forget about the two. It's just a conditional independence that you want. So that's it. So instead of saying conditional independence, you're just giving us the sufficient conditions in
graph. That's all. Yeah. It's not that they just formally reasoned out. It's not the calculation was one line. There was nothing, but it's nice. But now it ties everything together. All this, now you can see why yesterday we spent time thinking about all this deseparation. Because now I don't need to check algebraic properties. I don't need to check whether those conditional properties are, I don't need to test all that. I can just look at the structure of the graph and decide what is. That's why this is useful. And this will give you nice theorems in a second. Okay, this view. So finally, the main theorem on valid adjustment sets. Okay, this is proposition 6.41 in text. So there are now, if I've claimed that something is a valid adjustment set, then I need to test for these two conditions. There are several others. I'm just listing two which are easy to discuss. There are other ones as well, which I'll let you read about how to find other adjustment set. So the first adjustment set, so the setting is the following. I have a node on which I'm performing interventions. I have a target somewhere downstream where I want to, that's where I want to measure. I want to measure in the new world. And all we have done is to add this one node to the graph. The first adjustment is called parental adjustment. Suppose Z are the parents of XK, then Z is a valid adjustment set. Let us check why. Okay. So we need two conditions. We need, first let's look at the simple one, Z and I are independent. Z is these two, I is here. Are they D-separated? Yes, because XK is a collider. Okay, so there's a collider, so they're D-separated. So that's that. Now what about condition? Condition on XK and Z, XJ and I should be D-separated. This and this should be D-separated, condition on this. Let us see. So I'm conditioning on all these three, and we want to check for D-separation of these two. Well, conditioning on this blocks this path. Conditioning on this unblocks this path, but then adding this back closes back those paths. And so you can't continue. Okay. So this is a valid set for satisfying those three properties. So this also goes back to the question that I think you asked, what should be a valid adjustment set for your exam? This is called parental adjustment.
So you had a result yesterday, this parents of the same parents. So this is essentially that.
It all comes back to that. If you condition on a collider, you need to close it elsewhere.
Sorry, could you repeat that last part? The proof of the second part, the conditional.
The comment or okay, let me just.
No. When you argued that.
They two are okay. I see what you're asking. So there are two parts, right? We want to check Z and I are D-separated without any condition. Wait, I want to argue Z and I are. So I want to argue this and this are independent. That was one condition.
Yeah, that's
are
easy.
They D-separated? That is because of XK, right? XK is a collider, so we cannot. These are, and I has no parents, so we cannot go this way because there's a collider on the path.
That part was clear, but the second part was
the second part. I see. Okay. Now the second part is this one and this one should be D-separated, condition on these three.
Yeah.
On XK and Z. So now let's see why. So let me choose a color. I'm just going to draw this as a conditioning set. Okay. So from I, first let's look at the direct path from I to XJ. This is the direct path.
Yeah.
Because XK is there in it, it's blocking that direct path, so we cannot go directly.
Yeah.
But maybe you can go other ways.
Yeah.
Because this is conditioned on, remember, if I condition on a collider, then it opens that path up. So now, because this has been conditioned, this path has become open. So if I did not have any of this in the set, then I could go this way.
Yeah.
But because I have this is blocking that path. This one is blocking this opened up path.
Okay, got it. Okay.
And this is also blocking any other opened up paths.
Yeah.
Okay, so that's what I'm saying. Okay.
Thanks.
So conditioning on XK and disease blocks all paths. Okay. So this is called parental adjustment. So this is the valid adjustment set. These parents. Yes.
Could you give an example where B is true and A is false?
Where B is true.
So I mean let's say Z graphically, conditionally, independent of I.
Yeah, okay, I can give you an example. Okay, you want you want something that is not an adjustment, but nevertheless this is true. And here's the example. Suppose I just condition on this on one of its parents. Just give me a second. I do this as my condition. Now, this thing blocks from I to XJ. this one. But this one has opened up the path from I through xk through this leftover LO thing all the way to xj. And I'm not conditioning on that. So if I just chosen these two as my, if I chosen only this node as my adjustment set, then that wouldn't work. Only B is true, not A.
I think my question is, if I find a set where the second statement is true.
This is the second statement.
Yeah.
It's not enough.
What?
Oh, okay. Now you're asking why do we need this at all? Why is that your question? Why is this condition required?
Yes, I feel like in atomic interventions on single variable.
No, the reason it's required, it's sufficient. I don't want to say it's necessary. The reason it's sufficient is goes back here. We have that term and that term. This is my total probability theorem. I am saying that this is equal to this and this is equal to this. So I need for that to, I am trying to get every term to match. That means I need these conditionals to match, these marginals to match. Is it
sufficient? Condition.
It's sufficient. I want this equality. And this equality is over summation. I'm asking much stronger condition. Expand this summation out for every single term, every element should be the same. Of course, you can get equality. All I really care about is this equality. Okay, maybe there's cancellations, other things. That's why this is a sufficient condition. It's term by term equality. Does it make sense?
Yeah, I think what I'm trying to say is if that is true, that sort of applies. So maybe I'm making a stronger statement in terms of just atomic intervention.
For this graph, maybe something happens. There are other. I'm giving you one. I'm just giving you sufficient conditions. That's all. Nisha?
So maybe you already answered my question. I was just thinking maybe it is also necessary. Can there?
It is not necessary. It is not. I'm going to come to that in a minute. Let me do some sufficient, then I will. So I'm trying to motivate through all this something called do calculus, which actually generalizes this to give necessary and sufficient conditions. Adjustments are just sufficient conditions. Okay. So next, the backdoor criterion. Okay. That's another criterion for again another sufficient condition. Suppose for some reason you don't have access to the parents, or you cannot. You know there are parents, but you don't have access to those variables. What can you do? Well, backdoor criterion says the following. I want to find a valid adjustment set, which is different from where you're intervening and the target. So this is a picture. This is where you're intervening. This is where you're doing the target. Okay. This is where we are intervening. This is the target. So backdoor adjustment has Z contains no descendants of xk. I'm going to, so this red is not allowed. That's why I put a red. I'll reason why this is true. First, I'll state the rules and then I'll reason through it. So this red colored thing is not allowed. And Z blocks all paths from xj to xk. From X, it blocks all these paths that passes to the parents of, oh, XJ and XK are mixed up. Sorry, there's a typo here. Okay. Z blocks all backdoor paths. Backdoor paths are those that start from I and go through the parents of xk. Okay, that's what is called a backdoor path. So this is a backdoor path in this. If there's something else here, that would also be a backdoor path. Okay. This is not called a backdoor path. If it's going, it has to, a backdoor path is a path that goes through parents of the xk. That's what is a backdoor path. Okay. So now two statements. Z contains no descendants and blocks all backdoor paths. So let's see what happens. First ignore the orange. Let's just make sure the two conditions work. Then I'll put in the orange and say why that is needed. Okay. So we need I and xj to be independent. What are we conditioning on? The conditioning set is the first is the second. I and z should be independent. That's the second condition, correct? Without any condition. That is true because there's a collider. Okay. Now,
the independence comes from not having dissonance, right?
Which one? I want to check Z and I are independent.
Correct. And that is true because you're not already dependent.
There's no calcul. Yes, exactly. Exactly. That's all. So if this was also part of Z, that would be a problem. Okay. If I put Z was here as well, then this path is there. There's an issue. Okay. Yeah. Oh, you're answering the right question. I see. Yeah. But for anything on the parental side of Z, it's fine because this xk itself is a collider. Then that's condition B. Condition A is condition on Z and xk, I and xj are deseparated. So this is condition, so it's blocking all downstream paths. This is the only upstream path that is blocked here. The condition on this opens this path, but then when it hits Z, it's blocked. So that's the black door criteria. But this is called the backdoor criteria. Question.
What will happen if there is an edge from C to red?
Suppose this was there.
Yeah. Then there is no backdoor. Right?
Suppose this is there. Yeah. What is your issue? So this is still, these two, this and Z are they separated? They are, because of this, the collider. This becomes a collider. We are not conditioning on the red. That's a collider. Okay.
Sorry, the backdoor path you said, it's like any path, it's in the undirected path, right?
Yeah, but which goes through the parents of xk. A backdoor path is an undirected path starting between I and xj that goes through the parents of xk.
So if like C, for example, is a collider.
Z is not a collider. Oh, it cannot be because it's not. It's on this path. It's not a collider. It's a path. How will it become?
Like there's two things. So if you condition on that, then it opens the path, right?
This is a DAG. You're basically saying I want to change this direction this way. Okay, let us see what happens here. So this is your graph and you want to condition here. And what happens? Now, I want to condition on Z. Let us see, is there a cycle here? This.
If I guess in this case, Z doesn't block the original backdoor path.
Yeah. So this,
if that arrow is reversed, Z doesn't block the original path. So it doesn't fulfill the other requirement.
Okay. Okay. Thank you. Okay. I guess he answered it. Z blocks all backdoor paths. That is the condition on Z. Okay, you can't choose any Z on it. It needs to be a Z that blocks the path. So that conditioning will not block the path. Okay. Okay, so this is the backdoor criterion. There's yet another criterion. You see, this is all just graphical reasoning. Okay, what we have done is, that's the nice thing about adjustments. Now, in the last 5 minutes, I'm going to tell you what do calculus is, but I'm not going to go through it. because it is quite messy. I'm just going to tell you very high level what is going on there. Okay. What we'd like are, again, going back to the basic question, compute interventional distributions from observational distributions. Adjustments is one way. Look at every term and ask them to be the same. But clearly that, well, not clearly, but it's not at this point whether that is really needed. Okay. And so can we, the only question we care about is, can we compute on some target variable y, and I do something on x, I want to compute purely using observational distributions. We want some factorization. We may not even use total probability theorem. We want some way of using those values which you can compute to patch it together to compute this. And do calculus provides a set of rules that allows manipulation of conditional distributions in in the observational model to try to get things for interventional models. So this is at the core of Pearl's framework for causality. Please read the book for actually the details, or Peter's book for abridged discussion. This is even more abridged, meaning I'm not going to explain anything. I'm just going to state some rules which are very opaque, the way I'm going to say it, and say there are manipulations that can be done. My statement is just a little bit more than there is something that can be done. Okay, I'm not going to say much beyond that. Okay, that's the honest answer. So given those caveats, let me state the kinds of rules we are looking at. Yes?
You don't need to have any valid adjustment set.
No, I'm going to tell you, no, you don't need adjustment sets. But you need certain, so adjustment sets was a way for getting certain conditional probabilities to be the same. Now I'm going to tell you certain collection of conditional probabilities that happen to be the same. Okay, that is what do calculus says. And then you figure out how to use those to find what you want. Okay, I'll do it I'll answer your question a little better in a minute. Okay, so what do we have? You have an SEMC. You have the graph G. X is where the intervention is being done. Y is a target. Z and W are some other sets of nodes. That's my generic notation. X is where intervention is being done. Y is the target. The first rule is the following. Suppose that Y and Z are d-separated given X and W. Okay. Suppose this is true. In this graph G tilde, where incoming edges to X are removed. This makes sense. This is where X is where you are doing the intervention. Okay, so deleting those edges is something we can look at that model. What does this mean? Now I have this is essentially a particular interventional model where I am intervening on X, right? That's what this is. And suppose in this model, Y and Z are d-separated given X and W. Then this is called insertion deletion of in that world alone. This is not relating two different worlds. In that world where you do X equals X, the conditional of Y given Z and W is the same as the condition of Y given W. You don't need to condition further on Z. That's a statement. Okay. I'm just going to give you a sort of, I'm not proving any of these things. I'm just giving you the rules of do calculus. Okay. This is one set of rules.
It's just conditional independence, right? There's nothing here.
Fine. I'm not going to. Fine. Whether it's conditional, I'm just going to state a collection of rules. Whether they're obvious or not obvious, or just conditional or not conditional, I'm not making any statement. I'm just going to go through. This is called insertion deletion observations. Okay, because Z is quote unquote. Whatever. The second rules are called action observation exchange. So now look at yet another graph where incoming edges to X and outgoing edges from Z are removed. So this is, whenever you do such a thing, you have some other distribution. So I've moved to a third world, okay, where we have done some other surgery on that graph. In this world, the following is true. Suppose Y and Z are d-separated in this world. Then in the world where you do on X and Z, look at the conditional probability of Y given Z. That is the same as the conditional probability in the world where you only do on X, but you condition on Z. Okay. Again, I don't expect you to parse any of this in real time. I'm just stating the kinds of rules that are there. It's giving you a set of manipulations you can do. Think of a world where you have the observational, and there's one intervention. There's all sorts of other worlds floating around where you can do various graph surgeries. What these are telling you is how conditionals on one world are related to some different condition on another world. So now you have a whole bunch of equalities, and can you somehow zigzag through this to get what you want? Okay, it's not this one step equal. You say, oh, I can't get this to be equal to this, but maybe this group will become something through some zigzag. Okay? That's what do calculus is trying to do. Third.
So when I do a variable, I remove the incoming edge, but how do you remove the outgoing edge?
I'm telling you, this is a new model. I'm not telling you how to do it. These are all thought experiments. Remember, I am not actually doing any experiments. I am giving you a whole world of thought experiments. So I can do a thought experiment. That's a different graphical model.
Yeah, but from the formula, it seems like you remove the incoming edges both on X and Z variable because you are doing.
That is for G hat, but this is not about Z hat. This is, so suppose this and this are deseparated in the world where these are removed. Then in the world where this is not, where the incoming edges are removed, this conditional deseparation is in the world where incoming edges to X are removed and outgoing edges from Z are removed. If that is true, then in a third world where incoming edges to both X and Z are removed, yeah, conditional distribution is the same as the conditional probability in the world where only incoming edges of X are removed, but you condition on Z. So you see, these are statements about multiple worlds, okay? This world is not the same as this world. I'm just giving you a bunch of, as I said, I'm not going to explain what these rules are. I'm just telling you the flavor of these rules. That was my caveat in the beginning. Okay? The third is even more messy, so I'm not even going to explain it. It's so messy to even insertion and deletion of actions, it's called. It relates worlds in even more bizarre manner. Okay. Suppose the point is these rules are complete, meaning all identifiable intervention distributions can be computed using these three rules. Okay, that's the punchline. And there exists an algorithm by Tian 2002 that can use these three rules to find all identifiable distributions. Okay, what do I mean by identifiable distributions? Meaning, suppose you want to compute a particular intervention probability and your observational data. Is there a way of translating those interventions? This is a fundamental question, right? I have all this data. Can I compute this or not? This answers in the positive. Yes, these are the three rules. There's a way of composing these three rules together so that that can be done. If at all it can be done. Period.
In particular, there are some interventions that you cannot compute.
Of course.
You have to do.
Exactly. Of course. There are some. I'll give you a simple example. Okay. Take a graphic structural equation model, change every equation, and make a new. I mean, I know I'm being silly, but make a new model. There's no hope of going from one to the other.
Oh, wait, here are we talking about like one variable intervention or what kind of interventions are we talking?
This is, I've written it in sort of target X and Y, but there are other forms as well you can think about.
Yeah, so going back to the question earlier, so all these rules are about identifiability, right? So you want to calculate some causal probability from observational data.
Correct.
Many choices on Z. If they satisfy these conditions, you can calculate.
It's not even Z anymore. This is not even Z. There is no Z either. Okay. This is just.
So you can select some confounders, which you condition and you can calculate. But does it say like what kind of? You have many choices.
This is that's Tia. So there are many choices. First of all, there are multiple. You can find, if you find an adjustment, you can do it. I'm not saying any. They'll all give the same answer. So in the infinite sample setting, in the distributional setting, nothing matters because you have access. Choose whatever you want. Of course, right? Because you have also concentrations as well with finite samples. We have to start worrying about various other issues. Okay. In this case, in the infinite sample setting, it's the distributions. It's just equation. We are playing with equations. Algebraic equations here. Okay, as long as you find one way to compute that, you're done. And there is at least one way using this. Okay. So I want to, the last 2 minutes, I want to state one last thing before I close. So these rules have been, so beyond adjustment, what can you do? Why are these rules more powerful than adjustment? I've just been saying it is more, but not given you an example. The famous front door criterion is one such thing. So suppose I have X, Z, Y. I'm doing an intervention on X. I want to compute the effect on Y. But there's a U which is not observed, which is affecting X and Y. So now remember, I had my intervention here. This was what is going on. Now, if I don't know what to, I don't know how to find a good adjustment set because there's always a backdoor path, whatever I do, because I cannot close all backdoor paths. So adjustment sets will not work. In this case, can something be done? The answer is yes. The front door theorem is not looking like a total probability theorem at all, but something else very bizarre. It says, if I do on X, using those do calculus rules correctly, you can derive this particular expression. The key thing to note is every conditional probability here is from the original system. But this is not a total probability theorem anymore. It is something else. Okay, and this is called the front door theorem. So, so it is. I think this is a good place to stop for today. And to summarize, therefore, what we have done is talked about interventions and identifiability. So with this, I am stopping with sort of the forward model. Tomorrow, I'm going to switch directions and start learning, which is learning how do you learn causal models. So that's what tomorrow is about. Thank you.